Hello and welcome to CSE 228. Today we have a special guest lecture. So our speaker today, Nikhil, the CTO at Bluespec, was formerly faculty at MIT. So Bluespec, for those who are unfamiliar with it, has been, it's an interesting language. So in this course, of course, we've used Chisel. Chisel originated as a grad student language, has some additional enhancements from Sci5, but has a certain level of robustness. Bluespec, by being both older and much more supported and adopted by industry, has another level of robustness. It's kind of fun to see what that's like. Number two, that's some new abstractions. That's what we're kind of excited to hear about is some of these new abstractions and not just Verilog++, but how do you actually do some cool things and make it more productive or more correct. And so with that, I'll let Nikhil take it away.
Okay, thank you very much, Scott. Let me share my screen. Okay, good morning to everybody and greetings. I'm going to talk to you about Bluespec today, which is actually a pair of hardware design languages. And one of them is called BSV, one of them called BH, but I'll tell you more about that in more detail as we go along. Okay, so here are the key points on one slide, and I'll just repeat this at the end also just to reinforce it. It's a general purpose high-level hardware design language. It's general purpose in the same sense that Chisel or Verilog, System Verilog are not application specific, therefore designing any kind of digital circuit you want. There are two alternative syntaxes, which is there for historical reasons. One called BSV, which is System Verilog-ish, and BH, which is like Haskell. In this talk, I'll stick to the BSV syntax, but both of them are available and in use by various people. As Scott said, it's been in the field as a commercial product since about 2004, 2005, almost a little over 20 years. In about 5 years ago, in 2020, we stopped offering it as a commercial product and just made it free and open source. So for the last 5 years, it's a free and open source tool and language.
Nikhil, I'm sorry to interrupt you. Right now, the screen sharing, we're seeing maybe your terminal. I don't know if you're sharing the right desktop.
I'm not. Sorry. My mistake. Let's try that again. Just hang on one sec. Let me stop all the sharing for a second. Oh, okay, let me go into screen sharing again. Okay, sorry. Pardon me for being a klutz on this. Try this again. Desktop number 2, share. I have 2 screens and I think I shared the wrong one. Are you seeing a window with some slides on it now?
Yeah, we see the window. Okay, great. You're zooming in. Perfect. Thank you.
Yeah.
Looks good.
Okay, my apologies for that. Yeah, so these are the key points I want to make. I said some of these things just now. It's been open source for about 5 years, since about 2020, and you'll see in more detail, it uses ideas from Haskell for what I'd call circuit description or structural correctness, and it uses ideas from guarded atomic actions for what I call circuit description, so circuit semantics or behavior. I'll be saying more about this as we go along. Okay, so actually, maybe I will go into slideshow mode. Just hang on. Slideshow mode. There's a bunch of resources, compilers, libraries, IP, textbooks, tutorials, etc., which I'll give you URLs as we go along towards the end of the talk. Okay, so let me start by, first of all, giving you sort of very high level. The first question everybody asks is, so what's different about Bluespec? How does it compare with Chisel or HLS or Verilog or System Verilog, etc.? So let me first set the stage using this slide. Anytime we're using a hardware description language, you can think of engaging in two activities. One of them is circuit description. What are the pieces of the circuit? How do they connect together? So you can think of this as a static structural description of the overall circuit, which could be a complex system, but this is how everything fits together. So that's the circuit description part. And the second part is once you describe the circuit, then how does it evolve over time? How does it behave? What happens over time? So in PSV, you can think of these two parts as shown on this slide. For the circuit description part, we borrow ideas lock, stock, and barrel from Haskell. For one of the two languages, BH, the syntax is actually exactly Haskell, but it has the full power of Haskell, pure functional programming, powerful type system with algebraic types, polymorphic types, type classes for overloading, monadic types, the works. It's really everything you see in Haskell 98, although it's not Haskell, but all the ideas are taken from there. We borrow a little bit from System Verilog, which is basically syntax for the BSV variant of the language, which basically specifies things like packages and name visibility and notation for parameterized types and notations for parameterized modules and things like that. New things that were in Bluespec that were not in either Haskell or System Verilog is one is that the type system was enhanced to do very precise bit width specification and matching. So when we're designing with hardware, of course, we're using all kinds of different bit widths, etc., and we use just enough bits to hold whatever state we want to hold. And we have to be very careful about truncates and shifts and overflows and things like that. So we capture all of these in static types in the type system and make sure that we don't silently drop bits or add bits and things like that. The other thing we do is that, which is new also compared to the earlier Haskell and System Verilog, is that we support multiple clock domains, multiple clock and reset domains, but we also do static domain checking so that it's impossible to have signals crossing clock domain boundaries without going through a synchronizer, etc. So all of that is structural, how you fit together circuits. And I'm going to show you examples so that it all becomes a little more concretized in your head. For circuit behavior, we use something called guarded atomic actions. And that's not a new idea. It's been around since at least the 1950s or 1960s. And I've mentioned on the slide there TRSs, TLA plus, Unity, Event B, etc. as some of the languages usually in the software space that have used the same idea for concurrent atomic state changes. And to that, the innovations within Bluespec, the languages are that we can build these atomic actions in a modular way. That is, we can structure our circuits with modules just like you do in Verilog or System Verilog. And we can have these atomicity properties, which are global properties, built up incrementally as modules are connected to modules so that they still are atomic with respect to global state, which might be spread across multiple modules. In addition, we can also do, for practical use, we can import Verilog, we can interoperate with Verilog, we can import C. So for simulation, you can write pieces that happen to be implemented in C if you like. So these two major flow into the languages PSV and BH. The original ideas on using guarded atomic actions started off in a PhD thesis at MIT in the late 1990s. James Ho was the PhD student. Professor Arvind was his advisor. And James Ho right now is a professor at Carnegie Mellon University. Arvind unfortunately passed away last year, but until then he was a professor at MIT. The original ideas on circuit description, that is structurally how you piece things together, were due to Leonard Augustin, who worked with us at Sandburst initially and Bluespec after that, way back in the early 2000s. Okay, so let me just quickly compare at a 30,000 foot level what is different in what I just described compared to how Chisel works, right? And again, I'm not an expert on Chisel. You folks are experts on Chisel, so if I say something wrong, please feel free to correct me on that. So for circuit description, your Chisel uses Scala, right? Basically it's an embedded language within Scala, and you're using the Scala engine to do static elaboration, to connect things together, etc. So the Scala execution is about plugging things together in disciplined ways so that you can describe your circuit. And you can use all the power of Scala, syntax, functional programming, type system, etc. as you go along there. When you describe a circuit, ultimately the circuit behavior is in some sense no different from, say, Verilog or system Verilog. It's standard clocked digital logic. So these are the two ways in which you can see BSV is a little different from Scala. So on the circuit description side, it's kind of accidental. We happen to use Haskell, and Chisel happens to use Scala. You could flip those. They would be just fine. Both languages would be fine if you did that. But the idea is basically the same, to use modern functional programming language and its type system to do this. The lower thing about circuit behavior is going to be very different. So I'm going to be focusing a little bit on that as we move forward in this talk. The other minor distance, a technical difference, is simply that we don't actually use Haskell in implementing BSV. In other words, the compiler that we have for compiling BSV or BH into Verilog is a standalone purpose-built compiler for BSV and BH. It's not embedding it within an existing Haskell system or anything like that. We're just borrowing the ideas from Haskell. We're not using any Haskell system directly for that. Okay, I'm not sure I can clearly see any questions or something, so please speak up if you have any question at any point you like.
Will do.
Okay. Another quick little comparison. I'm sure you get asked this question, what's the difference between Chisel and HLS, etc. And this is sort of my take on these things, on at least two aspects about it, which is, if you think of the computation model, what is the programmer thinking about? What's the mental model in your head about how circuits execute? In BSV and BH, it's guarded atomic actions. In Chisel, Verilog, system Verilog, it's clocked digital logic. In HLS, you're not thinking in terms of hardware at all. You're thinking in terms of C or C++ execution. A very different computation model in HLS. And then when you think in terms of microarchitecture, BSV, BH, and Chisel, Verilog, system Verilog, these are all what I call hardware description languages. In other words, in your code, you are actually describing the circuit that you want, exactly the circuit you want, no more, no less. So there's no sort of surprises about what microarchitecture you might get or what state you might get or anything like that. Whereas in HLS, the microarchitecture is something that is created by the compiler. And actually, the user may not have much knowledge about the details of what's going on in the microarchitecture at all. So this is a very quick high-level view of where I think BSV, BH, and Chisel, and HLS, and Verilog, and system Verilog, etc. fit.
Did you have a question?
Yeah, so I'm looking at this chart. Can HDL do both guarded atomic actions and clock digital logic, or is it exclusive to the computation model?
Scott, could you repeat that? I can't hear very clearly.
If I'm understanding the question correctly, like,
are those both things Verilog can't do for the computation model?
So yeah, so basically, I guess the notion he's saying is, looking at HDL as Verilog, the question is, can it do clock digital logic and guard atomic actions?
Well, the abstract view, and you'll see it in the examples I'm going to be showing you. The designer, the hardware designer, is thinking in terms of guarded atomic actions, right? So first of all, let me first separate out the computation model of the vehicle you're using versus the computation model of what you're describing. Even in Chisel, Scala has its computation model, right? And that's not the computation model of the hardware. That's just the computation model for how the hardware is elaborated for you. And the hardware then is just a standard clock digital circuit. Similarly, in BSV, everything to do with Haskell is not the computation model of the algorithm you're implementing in hardware. That's the computation model of how hardware is elaborated and described. Once you describe that hardware, then the behavior of that hardware in standard clock digital logic in Chisel and Verilog, etc., you think in terms of clocks and or processes around clocks, and within clocks you're updating state, etc. That way of thinking is replaced by thinking of in terms of guarded atomic actions in BSV and BH. I'm going to be showing some examples in a fair amount of detail, so hopefully it should become clear, but please re-raise the question if it's not clear. Okay, so let me go into guarded atomic actions. And as I mentioned before, it's not a new idea. It's a very common choice amongst people in the community that do formal specification of concurrent systems. Going way back to Edgar Dijkstra in the 1960s, he had something called guarded commands. Term rewriting systems is a general mathematical concept that has been around for a long time. Specific languages like TLA Plus from Leslie Lamport, Unity from Mani Chandy and Jaidev Mishra, Event B, etc. So we're not inventing a new idea. Most of these previous applications of guarded atomic actions has been in the software space for concurrent software, and the innovation in Bluespec is to apply it to hardware. But the basic semantic ideas are exactly the same. Okay, so what do I mean by guarded atomic actions? So you can think of a system as some collection of state elements, registers, FIFOs, SRAMs, memories, things like that. And the behavior is given by a set of rules, where every rule has two parts. One is a Boolean expression, which is called the condition of the rule or the guard of the rule, and a body of the rule, which is called the action, which is what can update state. And the overall execution semantics of a guarded atomic action system is what's shown on the box on the bottom left. It's extremely simple. It just says pick any rule whose condition is true and perform the actions in the body. And just repeat this over and over again. Of course, when you do that action, some conditions that were true may have gone false, some conditions that were false may have gone true, etc. So next time around, you may have a different set of rules from which to pick, but doesn't matter. Just pick any rule you want and then perform the action. It's extremely simple and it's very powerful. And and like I said, all these previous languages have been, you can see some wonderful papers and textbooks on proving formal properties of correct when you have this system. And I'll explain a little more why it's powerful in just 1 second. Before I go into that, first of all, what I've described to you is extremely sequential, right? It's one rule at a time. Equivalently, you can execute it concurrently, many rules at a time, as long as you execute any action for any rule atomically, right? So basically, the idea is that the action of a rule may perform many state updates on many state elements. And if you take two different rules, they may overlap in the state elements that they examine or which they update, right? And by atomically, what you mean is that the actions of this rule must entirely precede the actions of that rule or vice versa. So that you never have to worry about interleaving of the actions of rules. So as long as you do things atomically, you can execute it concurrently, but it's for reasoning about correctness, it's fine to think of it even sequentially as one rule at a time. Okay, so why is this useful? Well, in general, for reasoning about correctness, about concurrent state updates, whether it's in software or hardware, atomic transactions are really extremely powerful, perhaps the most powerful tool for reasoning about correctness. And why is it powerful? It's because without atomicity, you get a kind of a cross product of all the different processes that are trying to access the shared state. And you have to think of all possible interleavings, and your head starts hurting very quickly. And it's very difficult dealing with it. The moment you say that the transactions are atomic, then you can think of them one transaction at a time. That is, you don't have to worry about interleavings anymore. So you can look at individual rules and ask about individual rules. Are they preserving the correctness before the rule and after the rule? if I was in a correct state, will I remain in a correct state at the end of it? So this is the extremely powerful nature of atomic transactions, and this is what we're exploiting in GAAs. The other aspect of a GAA, which is very interesting, is that the same language, the same vocabulary can be used at different levels of abstraction. You can write big fat rules that you can think of as a specification of the system you want to implement. And you can write much smaller fine-grained rules that are more realistic for hardware that actually represents the implementation of the hardware that you want to do. And because you're working in the same vocabulary, it facilitates the idea that you can now ask about equivalence between specifications and implementations and do proofs of correctness. You can do informal reasoning, but also you can also use formal tools for that process. And you can think of design then as a refinement process, often a refinement process where you can start with an approximate specification level view of rules, and then you can replace them with more finer grained things. I'm going to give you a very specific example to give you a sense of why this happens. Okay, so the comments at the bottom of the slide are basically saying we think of these in this way informally all the time while we're designing hardware. But some researchers have also taken it into the formal verification and formal correctness space by embedding these ideas in proof assistants like Coq and Lean and so on, and doing exactly what I said here on the slide in a formal sense. And then prove correctness of pretty complex systems out of order CPUs, distributed coherent caches, and so on. Okay, so let me give you an idea of what this looks like. I'm going to describe a small toy cache coherent system. It's toy because it has only one location in it, one memory location. So we're not going to worry about addresses here. Just think of having two CPUs, A and B, each of which can send memory requests and get memory responses to a local level 1 cache, L1 cache. And behind the L1 caches, which are private to each CPU, imagine that there's a shared L2 cache behind it. And imagine that it's in the state as shown out here, where there is the L1A has the cache location in exclusive mode, presumably because it wants to write it. And let's say it has written a value recently, so that value is X. Before it got there, it must have received the value from the L2 cache, but by this time the L2 cache value may be stale, so that's why I called it Y. It's the old value. But in L2, I also have a tag which remembers the fact that I have given this out in exclusive mode to L1A. And the cache for L1B is invalid because the location is currently being busily used by L1A for reads and writes, so it's an exclusive mode. So just imagine that's the starting state. And now imagine that I get a read request on L1B. What do I want to do? Well, here's a one-shot transition that explains what I want to do, which is what I'd like to do is to downgrade the exclusive L1A to a shared state, update update the L2 to the new value X and so that it also knows that it's in the shared state, and update L1B now to the shared state with X. And now that I have it available in L1B, I can respond that X to the CPU request. So that's the state transition at a very high level that we would like to bring about. Now this can be expressed directly in BSV code, as shown in this rule out here. This is actual BSV code that I'm showing you on the right here. So you can think of this part of the rule as the rule condition. It says this rule is enabled whenever this condition is true, and the condition says if this rule, just imagine what it's saying is if the requests, the first element of the request, its request type is a read request, and L1B's tag is invalid and L2's tag is exclusive, then perform the actions shown in the body of the rule, which is over here. So X is the value in L1A. I replace L1A with shared. I replace L1B with shared. I replace L2 with shared, and the fact that it's available at both A and B. And I enqueue the response back to the CPU with the value X, saying, here's the value X. So in a single rule, I express the overall state transition that I'd like to bring about using this idea of a guarded atomic action here. Okay, and the entire behavior of the cache can be expressed using such rules. So I've given you one such rule. I'd need, of course, a symmetric rule on the L1A side. I will also need other rules that express what happens if I get a write request. If I get a write request, I already have it exclusive. If I have a write request, but I have it shared. If I have a write request, but I have it invalid. Each of these situations, we can write a rule for the different conditions there and specify what transition we want on the rule. So it basically is a very high level specification of the transitions that I would like in my cache coherent system. The interleaving is not very interesting in the following sense that, I mean, the external triggering events are these read and write requests from the CPU. And because we choose one at a time, it doesn't matter. So imagine I have requests here from A and I have requests here from B. They both are sending in reads and writes in some non-deterministic order. It doesn't matter. Whichever one, I can pick the rule that matches and do the transition, and I can start proving properties of correctness of this cache system at this level of abstraction. And what do I mean by correctness? You can imagine correctness properties along the lines of, well, if it's exclusive in one of the L1s, it must be invalid in all the other L1s. If it's exclusive in one of the L1s, then L2 must be in the state exclusive pointing at me, and so on and so forth, right? You can imagine writing a bunch of properties like that, and you can ask for every such rule, if this state was correct before this rule, does it remain correct after the rule? And in that way, you can prove the overall correctness of your protocol at this level with rules at this level. So this code, as written, it's a little stylized to fit on a slide and make it clear, but I can compile this with the BSC compiler into Verilog and simulate and synthesize an entire system like this. But although it's fine as a specification, it's not very realistic as an implementation, because I'm doing sort of instant reads and writes of state that might be distributed quite widely on the silicon or even across different chips, right? I'm looking at the L1 cache, I'm looking at the L2 cache, I'm looking at the other L1 cache, I'm changing all their states simultaneously. In reality, you can only do things locally and you can communicate with the other elements in the system, but you can't really instantly change them. So we can write rules at a finer grain, which is a lower level of abstraction, using only local interactions, and send and receive messages through an interconnect to the other players in the game. So let me show you that view of the world. So again, we start at the same initial state, shown on the top left picture, and we get a read request from CPU B. And what we're going to do is we're going to do a local transition at the L1B cache, which simply says I'm going to go into a pending state and I'm going to send a message to the L2 saying, I request this please in shared mode. And that's expressed using this rule out here, which is a rule that's entirely local now to L1B. I'm only looking at things in or near or adjacent to L1B. Right? If I'm in invalid and I got a read request, go to pending and send a message to the L2. Okay, once we're in this state, I'm going to move this in my next slide. The bottom picture is going to move up, and we're going to take the next state transition. Okay, so here we are in this state. And now what we want to do is on L2, if we get a shared request and we are on exclusive, what we want to do is L2 wants to go to pending, and we send a request to L1A saying, please downgrade yourself from exclusive to shared. Right? So that's again expressed using this rule. The rule condition is the condition on the fact that I've got a shared request and I'm in exclusive mode, which is the situation over here. And these actions basically say I go to pending and I send a shared request over to the L1A. So let's keep going. Now in L1A, when I have a shared request coming in here, what I want to do is downgrade myself to shared, and I want to send a response back to L2 saying, yes, okay, you're shared, and here's the new value X. And that's expressed in this rule here. Move forward. In L2 now, when we get the shared X here, from pending, we can go to shared. I have a typo here. This should be X over here. Sorry. In L2, I've updated my value, and I'm sending a response back to L1 saying, okay, you can go from pending to shared, and here's the value X for you. And then we go forward one more. When we get the shared here, the L1B can say, oh, okay, I can now from pending go to shared, and I can get the value X, have my value X over here. Once I have reached this state, then we are in the cache hit situation, right? Which is I'm shared, I have a read request, so I have a hit, and I can respond back with X. And that can be expressed with another rule out here. So you can see how I've written using the same language, both at the specification level and at the implementation level. And it's a spectrum. It's not as if there are two levels. You can refine it through multiple levels, but you can reach a certain point where you can get a sense that the rules are entirely local to a module. They only talk about things inside the module, and they send and receive messages, etc., through interconnects of unknown latency. So another thing you can do is first level of proof of correctness ought to be that do these rules implement the cache coherence protocol correctly as given by the other rule that was given at a high level spec. So there's a whole proof methodology on showing so-called bisimulations between implementation level rules and specification level rules. And you can ask about additional questions like, does it matter what the latency is through these FIFOs here? Because it's an interconnect, which I'm modeling as a FIFO, but we don't know exactly what the latency is. There could be congestion in the network, etc. Can it deadlock, etc. Further complication at the lower level, which is not there in the upper level, is that both CPUs, for example, might give a request at the same time, one to L1, the CPU A to L1A, and both of them may start their engine for updating their caches. And these messages may collide, so to speak, when they get to L2, for example. And there has to be some way of resolving it, etc. So you not only are these rules more fine-grained, but you also have to worry about rules that are doing that kind of management of interleaving of messages that come out here. So all of which to say, it's not trivial to do all of this, but we have a language to do this, we have a methodology, and there's loads of theory behind these systems by the people who worked on term rewriting systems and all before to help us reason about correctness in this way. A different example here would be, let's say I want to prove the correctness of a pipelined CPU. Well, you might write one version of the CPU, which you think of as the specification of the CPU, which just literally does one instruction at a time. There's no pipelining at all in it. It's almost like the Spike simulator or something like that, right? But written with rules in this language. And the implementation level will have multiple stages. The decode stage will receive messages from the fetch stage and from the IMEM. It will decode it and send a message across to the register read stage, and so on and so forth. And you have the similar kind of question. Are these rules expressed at the implementation level doing the same thing, quote unquote, as the single set of rules that was done at the spec level? So there's a whole vast literature and methodology behind all of this, but this should give you a flavor of how we think in terms of behavior and actions in the circuitry, and how we crucially rely on atomicity of rules. Atomicity is very central to these rules. And the other thing about atomicity, it's not a local property. Atomicity is a potentially global property. So, for example, even amongst the rules that I specified here, you see some rules, for example, in rule L1B that are enqueuing into this FIFO. And you see some rules in L2 that are dequeuing from that FIFO. They're both going into the same FIFO. That is the shared state inside that FIFO between these two things. Is that going to work properly? Is there going to be some problem over there, et cetera? So the idea of guarded atomic actions is that you guarantee in the language semantics that rules are going to be atomic always. And then it's the obligation on the compiler when you produce code for this to make sure that you respect that atomicity so that any properties you reasoned about at the rule level also hold in the actual hardware that is created from this. Yes, somebody has a question up, please.
Question, yeah.
Hi, I have a question. So it sounds like the Bluespec can define a set of rules that describes the circuit behaviors. Suppose we have some bugs like race condition in the cache on the microarchitecture level, and can Bluespec detect this kind of race condition or other types of bugs in what level when we are compiling, or how can Bluespec find that or not?
Okay, good question. So first observation I want to make is that the race conditions can occur at different levels of abstraction, right? So for example, just imagine that I have two registers and no, let's imagine a single register and two rules that are both incrementing that register, right? So there's a read. Each rule is doing a read of the register and a write of that register. The atomicity here will guarantee that those two things can never interleave. So the register reads and writes will be completely atomic. So at that level of abstraction where you're talking directly about hardware element state, etc., there is no chance of getting a race condition by definition in BSV. But race conditions can, of course, also occur at a higher level of abstraction that is beyond the level of what the rules are directly saying, right? So in my cache coherence example, a rule is just sending or receiving messages. But now if you look at the trace of messages, you might see that the messages coming from two different sources are perhaps getting interleaved in some way. So now you're going above the level of the rules and all, and at that level, there's no defense against it. And this is true of any such system, right? Which is that whenever you're talking about avoidance of race conditions, you're talking about a particular level of abstraction. And what this is saying is that on all the hardware elements that I have here, whether it's registers or FIFOs or SRAMs, etc., a rule that may touch many registers, many FIFOs, many RAMs, etc., at that level, everything said in a rule is guaranteed to be atomic. So at that level of abstraction, everything is guaranteed to be atomic. So in general, when you're doing a design, all levels are of interest. You want to avoid race conditions, whatever the level of abstraction. So with the difference between doing an RTL level thing is that at the RTL level, even that lower level thing, you have to be very careful of and manage the atomicity there. And then you also have to worry about the higher level. In BSV, what you're doing is you're eliminating the lower level of abstraction where those race conditions can happen, such as what you're seeing over here. So let me show you another example where a little later on, where you'll see how atomicity can mess you up and how rules will help you avoid that.
I have a
Yeah.
question.
Yeah.
Also,
I was kind of interject. So for the issue of data race, I can imagine a scenario. Maybe it's not quite a data race; it's more of a scheduling question. If very simply, if I have one register and two rules with the same guards, and then one writes 0, one writes 1, how do I reason about the value of that register? Is it
Okay, that'll come up in just a moment.
oh great?
Yeah.
Cheng, do you have another question?
yeah, I think I can I can say my question in another way is that can we do because we have a set of rules, can we do reasoning where just like just like other theorem provers like Coq, can we do that in the Bluespec since you have a set of rules?
We don't have an automatic way of doing that. So there is a professor at MIT, Adam Shlipala, and students like Murali Vijayaraghavan, and they have done a model of Bluespec within Coq. So in other words, everything I've shown you as a rule here is almost directly transliterable into Coq, right? These are just simple expressions and data structures with rules and so on. And and they have invented a language called Kami, Kami, which is actually just if you like, a syntactic transliteration of this. It's sort of various technical reasons why they're not using BSV itself as their source language. It has to do with the way the compiler is structured and the difficulty of getting abstract syntax trees, etc. So what they've done is what they do is they manually take a rule like I've written here and write the same rule in their notation in Coq. And within that, they do their reasoning. So all their proofs of correctness about CPUs and caches and all that have been done within that framework. But in principle, absolutely, it's possible to take something like this and directly feed it into tools like Coq and so on, which know how to reason about thermodynamic systems.
Yes, thank you.
Okay, so to summarize, the kind of code I've written is not pseudocode. It's I mean, it might be pseudocode in the sense that because it's a toy example, I haven't actually coded it, so I may have made some mistakes in my code, but that is really actual BSV code, and that kind of code can directly be taken by the BSV compiler and compiled into Verilog. And that is all the behavior in BSV. There is no separate notion of processes or clocks or anything. Everything in BSV is expressed just using rules. And once the BSV compiler generates RTL, of course, you can then take that it becomes standard RTL, so you can take it towards simulation or FPGAs or ASICs or anything like that. So two syntaxes for that. I've shown you the BSV syntax. There is exactly the same thing can be written with a more Haskell-ish syntax, and there are some people who prefer that. And there's no explaining why people like Haskell versus Verilog syntax. So you find passionate people on both sides of that fence, but we say choose your weapon. You choose either one you like, and you can intermix them in a similar design. Some modules can be written in BH, some can be written in BSV, and because it's just a front end thing, they freely interoperate with each other. Okay, so let me now talk a little bit more about module interfaces. So you've already seen some use of module interfaces in the example. For example, in this code, here I'm looking at a FIFO, FCPU requests, .dq. DQ is a method that I'm invoking on the FIFO, which says, please, perform some action. Similarly, L1 is a register, and the dot value is a method I'm using to pull out the value from that. So the interaction between modules is just the standard kind of object-oriented view of the world. The additional thing we have with beyond just methods that you see in any software programming language are these two things. One is something which we call implicit conditions, which regulates when a method can be legally invoked. And the second is something called scheduling constraints, regulating how they can be called concurrently with the same clock, which will speak to the question that I think Scott just now asked, but we'll say a little bit more about in a second. And so note that up to this point, I haven't even mentioned clocks, and now I'm starting to mention clocks in this. Okay, so let me describe what I mean by this. So this is an example of an interface in BSV. It's an interface of a FIFO, and you can see the sort of system Verilog-ish notation that we use here. That is that a type hash parentheses is the parameterized type, just like in system Verilog. And so in this case, T is a type variable, so this whole interface is polymorphic. It's a FIFO of things of type T, whatever T may happen to be. And it has three methods in this case. An enqueue method, which takes an argument X of type T, and its type is of type action, which means it performs something in the FIFO, has some kind of side effect. Similarly, DQ takes no parameters, and it's of type action, so it performs something on the FIFO. And similarly, first is a method that is just a pure value method. It returns something of type T, which is the first element in the FIFO. Okay, so let's talk about what do we mean by implicit conditions. Implicit conditions are the idea that every method in BSV potentially comes with an implicit Boolean, which determines whether it's legal to invoke that method or not. Typical use of that is what you can see in these two bullets here, which is that enqueue should not be invocable if the FIFO is full. You can't enqueue anything more into it when it's full. Similarly, DQ and first should not be invocable when the FIFO is empty. There should be something in the FIFO before you can look at the first or DQ it from the FIFO. So what does cannot be invoked mean? Right, that's an English phrase I'm using. Specifically, technically, it means the following, that ultimately every method is called from some rule, right? I mean, you've seen that example here, right? Here's a method call, here's a method call, here's a method call. So methods can maybe called in conditions, they may be called in the bodies of rules itself. So ultimately, a method is called from some rule, or transitively from another method. So you can have a rule in one module that calls a method in another module, and that method may in turn call a method in a third module, and so on. So you can almost think of a rule like this giant spider. It's in the middle is the rule, and it's all these methods that it calls initially to adjacent modules, and the methods in those adjacent modules may call further modules, and so on. But ultimately, every method invocation is tied up to some specific rule. And all these implicit conditions in the rule are governed whether that rule is enabled to fire or not. To fire meaning can it be executed? Is the rule condition true? The kind of Boolean expressions you saw in the examples I gave are what we call the explicit rule condition. That is a condition that the programmer has specified as part of the rule. But in addition to that, we conjoin the conditions of methods that might be invoked. And the rule's overall condition, whether it can fire or not, is determined by the conjunction of all of these things. And it simply does not fire if the method is if the FIFO is not, if the method is not enabled. So as an example, in this picture here, the FIFO might be called, the enqueue method may be called from a rule over here, and the first and DQ methods may be called by a rule from here that's consuming things in the FIFO. The rule condition simply doesn't fire if either the first or the DQ is not enabled. And similarly, this rule condition will not be enabled when the enqueue. And all of this is internals. We call it implicit conditions because the compiler takes care of all of this. You don't need to explicitly say any of this. So going back to this example that I had here, if you think of this rule, you can see that it's looking at first over here. It's looking at DQ over here on one FIFO. On a different FIFO, it is enqueuing something, and it may be doing more methods and other things, etc. And so this rule will not be enabled if, for example, if there was nothing in the requests FIFO, this part of the condition would be false. It would also be false if there is something in the FIFO, but either of these is not true. It also wouldn't fire if the output FIFO into which it's dequeuing does not allow it. So there is no chance in this rule that I might dequeue something from this FIFO and then discover that this FIFO is full and therefore I had to drop something on the floor because I took something out of this queue, but I can't put it anywhere. So the atomic transaction makes sure that everything is okay in firing this rule, including all these implicit conditions. So that's what implicit conditions are. And typically the net result you'll see is that BSP programs look a lot like this. They're almost like data flow graphs where rules are consuming things from registers and FIFOs and things and producing things into registers and FIFOs and RAMs and things like that. And and everything gets sort of, because of these implicit conditions, we rarely sort of think about explicit flow control, except at higher levels of abstraction, right? So for example, the normal, in the rules that I showed you, I never worried about whether FIFOs are full or empty or anything like that. It just all comes for free from the implicit conditions. At higher levels of abstraction, you might think of explicit flow control. Like, for example, if you have a long pipeline and you have some notion of a credit-based flow control that is now you're spanning multiple modules, multiple rules across multiple physical things like that. That kind of flow control, like a credit-based flow control scheme, would be something you'd have to code up explicitly. But at this level, it all comes for free. The second kind of thing we have on methods, in addition to implicit condition, is scheduling constraints, right? So let me explain what I mean by scheduling constraints, right? So let's look at our FIFO again. Let's look at a FIFO that's being produced from this rule and consumed from this rule. With exactly this interface, I can describe to you two different kinds of FIFOs with two different kinds of semantics, right? One kind of semantic is that what we call the pipeline FIFO, where conceptually in the rule-based view of the world, you're doing first and dequeue before enqueue. What does that mean? What that means is that suppose the FIFO is full. Well, you couldn't enqueue on it because it's full, but you can do first and dequeue. If you do a first and dequeue on it, then you opened up some space, and then the enqueue can happen. So I can give you a FIFO which has those semantics in the rule-based view of the world, that dequeue happens before enqueue, so such that in a single clock, I'm able to advance things through the FIFO. That is, simultaneously take out something from the FIFO on the right-hand side and put in something from the left-hand side. This is the typical kind of FIFO you'd have in a standard pipeline in the CPU, for example, where you're trying to advance every stage of the CPU simultaneously as you go from left to right, from fetch to decode to register read, etc. Right? So that's one semantic. The logical view, rule-based view, is you did a dequeue. So even though it was full, you could move things because you're taking a dequeue before the enqueue. The dual of that is what we call a bypass FIFO, which is, imagine that the FIFO is empty. Well, you couldn't do a first and dequeue normally on it, but you can do an enqueue. If you do an enqueue, now there is something in it, so now you can do a first and dequeue on it, right? And carry the rule follow. So if you think of a scheduling constraint as enqueue before dequeue, this FIFO has the property that enqueue logically comes before dequeue and first. And conceptually, in the hardware, if you think of it as a clock thing, the value sort of flies through the FIFO in the same clock. And that's why we call it a bypass FIFO. So what we are saying here is that the interface types are not enough to say what are the semantics of the FIFO. Both the interface is the same. The interface as shown on the picture here is exactly the same for both of them. It's the scheduling annotations on the schedule, which you can think of as a different kind of thing, like a type, is basically telling you which kind of FIFO this is being used. And these are, I'm only giving you two examples. I can come up with more examples of different kinds of FIFOs. Other kinds of scheduling constraints, an NQ can be invoked only once in a clock, or a DQ can be invoked only once in a clock. And Scott, going back to your question, if I had two different rules that were both trying to read and write a register, they would collide because of a scheduling constraint that says you can't do two writes into a register in the same clock. And that will be taken care of by the compiler to arbitrate between those two rules to make sure that that never happens. Another kind of thing is that two rules can never be invoked concurrently. They always collide. So in other words, they must occur on different clocks. So these constraints are something you do think about all the time when you're designing hardware. When I say you do, that is somebody has to think about it. And typically when you're working just with clock digital logic, you have to work out what you want to happen in each of these cases, and you have to produce the circuitry for it to do the right thing. And further, this detail, is it a bypass FIFO or is it a pipeline FIFO? It's not something that's formalized in the code anymore. It's formalized in the sense that it's represented in the code you created for it. But for somebody who's using your FIFO and who may not want to look through your code, nothing in the interface tells you about that. And what you might find is some documentation on the side that says, by the way, if you try to do a DQ and NQ on the same clock, this is what happens. All right. And so it might be in some ad hoc documentation. What scheduling constraints do for you here is that they formalize this in constraints that are known to the compiler and respected by the compiler while it is producing the code for this. So it starts with whatever primitives we have in the BSC library come with the scheduling constraints. So these primitives are, like all primitives, implemented by magic. And then any user level module that you define on top of that with its own interface and methods, the compiler systematically infers what scheduling constraint that implies on its methods and recursively up through the module hierarchy. And it takes care of all of these things to make sure that all of these constraints are respected when we produce the Verilog. So let me now get, yes, somebody had a question.
Hi. So I like this idea of formalizing the constraints. So what if suppose when you run the verification and you find that there are some corner cases or there are other constraints that should be met, and when you are designing it, you didn't imagine that, you didn't expect that. So in that case, will you add these constraints or corner cases into your program or not? Or can Bluespec automatically infer these hidden constraints?
Okay, so that's a good question. As I just mentioned, the constraints start with the primitives, right? And so, like in any language, the properties of the primitives are given by magic, right? So you have a plus symbol in your language. Does it really do addition? Well, that's the primitive. You have to make sure that the primitive does the right thing. But let's assume all our primitives have been given these constraints and those are all correct for the primitives. What the Bluespec compiler is saying is that when you build a system using these primitives, no matter how deep your module hierarchy, we will guarantee that we will never violate any one of those constraints in the final system, right? So it's making sure that constraint is preserved all the way through. Now, you may have kind of additional constraints that you might be thinking of. So one example is in the example that Scott mentioned earlier, I have two rules that are both trying to increment a register. Well, they both can't do it in the same clock. So what happens? Well, when you run it through the compiler, it will recognize the fact that the scheduling constraint is violated, and it will introduce arbitration logic to suppress one of those rules if both those rules are simultaneously enabled. If only one of those rules is enabled in any one particular clock, you can let it go. But if both are enabled in some particular clock, you have to suppress one of them. Delay one of them. Okay, which one do you delay? And what the compiler will do is, because the rule selection choice is non-deterministic, the compiler is free to pick any one of them. So it will tell you that I have a conflict between these two rules, and I'm prioritizing this one over this one because of this conflict of both trying to write into this register. Now, you may decide that for your application that you would actually like it the other way around. So one way to add constraints is we have basically attributes you can add to a rule which says, no, make this rule more higher priority than that rule, etc. So you can adjust priorities like that. There are other ways by which also you can add additional constraint on top of it. But what all the language is doing is it's guaranteeing that the minimal set of constraints, which is that no constraint on any primitive should ever be violated, that is guaranteed by the compiler.
Thank you.
Okay, so now let me show you an example that I hope will put together a lot of these different pieces that we have been alluding to. Haskell level types, Haskell level parameterization, Haskell level static elaboration, which you can think of as generate on steroids, which you also do in Chisel, right? You're using Scala, which is generate on steroids, basically. And also I'm going to talk about rules for complex flow control behavior. So the example I'm going to give you is a butterfly switch, which is illustrated on the picture on the right. And many of you might have seen such a picture before, or even designed such a gadget before. What's illustrated in this diagram is a 4-input, 4-output switch. So you can think of each of the inputs and outputs as a stream of packets. So a packet can come in on any of these input ports and leave on any one of these output ports. And if you follow these black lines, you will see that there is a path from every input port to every output port. So a packet can be routed to from any input port to any particular output port. Second observation to look at in this picture is that it's recursive. So what I've shown you is a 4x4 switch. But internally over here, you can see that I have two 2x2 switches that have exactly the same recursive structure as the 4x4 switch. So you can go in the other direction, make an 8x8 switch or a 16x16 switch, just following the same recursive principle that you see out here. When you get down to the base case, which is a 1x1 switch, those are the green boxes here. Think of that just as a FIFO, 1x1 switch. You have one input, one output. Just think of that as a FIFO. You can think of these yellow things as the routing functions that decide when a packet comes in here, whether it should go straight or it should go into which of its two outputs should it go out on. And you can think of these blue boxes as merge boxes, which basically have two incoming streams, and they somehow interleave those packets to produce a single interleaved outgoing stream on its outputs. So first of all, let's think about the interface for such a switch. And that's basically shown over here on the left for the interface of the crossbar. And I'm parameterizing it by T. So I'm not committing to what the type of the packet is that is actually flowing through the switch, because the general principles are the same no matter what the type of the packet is. And you can think of interfaces can be nested. So what you see here is that I have a nested interface called input ports, which is a list of put interfaces. A put interface you can think of as just like the NQ side of a FIFO. That is, you can put something into the module using a put interface. Similarly, the output ports is a list of get interfaces, which is the list of these output ports. Okay. Now, here on this slide, you're seeing the entire code on the left-hand side for the whole butterfly switch. And we're going to go through little pieces of it so that I can show you how to parse the code in your head as you go through it on the left. But this is actually the full code, compilable and synthesizable as is. Okay, so let's look at the pieces one by one. So starting at the top, you have the module parameters. The N is just the size of the switch you're looking for. You want to create an N by N switch, right? And like I said, you could do 2x2, 4x4, 8x8, etc. The second parameter is a function. So I'm passing a function, a higher order function, if you like, as a parameter to the module, which is the function that takes a packet that is an X of type T. That's a packet, and it gives you a number which says which output port is it supposed to go out of, right? So remember, I'm making the switch polymorphic on packet type, but the routing function needs to look inside the packet to decide how the packet should move through the switch. So that's encapsulated in this function called destination of. The third thing I'm parameterizing by is another module. So I'm parameterizing one module, which is the XBAR module, by another module, which is the merge 2x1 module. And that corresponds to these blue boxes. And why might I want to do that? Well, you can imagine that you have different blue boxes with different policies on how you merge. You might have a fair merge, or a merge that always favors the left, or merge that always favors the right, or something that does round robin. Least recently used. You can imagine different kinds of merge boxes. And rather than committing to that beforehand, I'm passing that in, that module itself, as a parameter. So you can see very powerful parameters of modules are possible, which is, again, no surprise if you're used to Scala or Haskell, but it is a big surprise for people who are not used to such languages. Okay, the next thing let's look at is the recursive module instantiation elaboration. So what we're seeing here is this is the base case if n equals 1, and this is the recursive case, else. If n equals 1, then we simply instantiate a FIFO, right? And then the input ports is just the singleton list of the put side of that FIFO, and the output ports is just the singleton list, which is the get side of the FIFO. If we look at the recursive case, what we see here in these two lines is we are instantiating the two sub switches that are of half the size, n over 2 size, right? So in other words, we're instantiating here exactly the module that we're defining here. So this is a recursive instantiation. Once we have that, then we can collect, then this line basically says, the merge module that you passed in as a parameter, I'm going to replicate it n times. In other words, I'm going to make n instances of this, and I'm going to collect them in a list. So that corresponds to this column of merge modules out here. Here are the two half-size switches. So those are the sub-modules of the overall module. And then I can, just using list appends and so on, I can collect all the input ports and output ports by appending together the appropriate things out here. So again, we are doing recursive module instantiation. You can write loops for module instantiation. Basically, you're seeing essentially the full power of Haskell being used to do circuit elaboration. Replicate n is a library function because it's so useful, but it's something you can write within BSV itself. Like I said, it's the full power of Haskell, so you can write replicate m yourself. If you don't have a high order function that's suitable for your purpose, you can write it yourself. Then finally, let's look at the behavior, right? So here, what I have is a loop, which is a generate loop, basically. And what I'm trying to do is I'm trying to generate all these yellow blobs that you're seeing in the picture here, this column of 4 yellow blobs. Each one is a rule that does a get from its input FIFO, uses the routing function to decide which of its outputs it should go on, and then does either a put on one output or a put on the other output. So that's basically what it's doing. It does a get, then it applies the destination of, then it uses Haskell-like pattern matching to decide what the outcome is, and then it does a put on one of its two output FIFOs. So you can see how in a very little bit of piece of code, you can express quite a complex piece of hardware out here within BSV. Again, no surprise if you're familiar with Haskell, etc., but it is unusual in hardware design languages. You can do this in Chisel, of course, but most other hardware design languages, you cannot do this. Also, the whole thing is flow control, right? And because I'm starting with primitives that happen to be flow control, in this case, a FIFO, and inside the merge module, assuming that's flow control, then the whole thing becomes automatically flow control. So I don't have any extra noise in my code about testing for emptiness, presence of packets, and things like that. Inside the merge module, I might actually test things like that, because if you want to do things like fair merges, etc., you may actually have to look at what's on your inputs, etc. Right. So
We have an in-person question if you don't mind.
Yeah.
Yeah, I'm curious what you mentioned like using the full power of Haskell for generating higher order functions and things like that. I guess how expressive is that kind of software generation within Bluespec, considering that it's not a embedded DSL like Chisel and so on?
Scott, could you repeat that again?
Yeah, I can repeat that. So you mentioned, using the power of Haskell to, express higher order functions to do useful things, but earlier you said Bluespec is not embedded in Haskell. So, how limited or how fully capable is that?
Yeah, so the Haskell has, of course, evolved over the last several decades. And if you think of Haskell 98, which was one of the milestones in Haskell's evolution, what we have here is from the lambda calculus point of view and the types point of view, everything that was in Haskell 98. It's a separate language by itself, but essentially the ideas are carried across exactly as is. Now, in Haskell per se, since that time, there have been further evolutions, including type generics and dependent types and those kinds of things. We don't have those in Bluespec, but essentially you can think of it as roughly equivalent to what was in the Haskell 98 spec, which is itself a very powerful language. We've in a different dimension, we've added things that aren't in Haskell, which I had mentioned a little bit earlier before, which is that we've added the idea of numeric types in the type system with numeric type matching and type checking. So, for example, you can precisely express the idea of concatenation of an m-bit type and an n-bit type, producing an m plus n-bit type. That's something that is statically type checked in the system. So that's an addition beyond what was in Haskell 98. I think you can do it in modern Haskell using things like multiple kinds, so-called kinds, which is another layer of above the type level is a layer called kinds. You have something called numeric kinds. I think you can do it in modern Haskell, but you couldn't do it in Haskell 98.
Great.
Okay, so I hope you've got a flavor of what it looks like to write, what code looks like as written in Bluespec. To recap, we're using Haskell ideas for static elaboration, for circuit description, as in this butterfly switch. The first level of code, if I go back to my overall code here, much of this is circuit description. The one place where we're talking about behavior is this piece, which is the rule, which corresponds to these yellow blobs out here. And so you can think of the static elaboration of this just like static elaboration in Chisel or Verilog or System Verilog, except now you can do recursion, you can do a very powerful parameterization, etc. And at the end of this, what you get, just like in Verilog, System Verilog, Chisel, you get a module hierarchy. And the one difference between this and those is in those languages, inside those modules, in Verilog and System Verilog, you have always blocks, which expresses behavior, right? Always at pos edge, do this or do that. If this condition is true, do this, do that. Instead of those, we have rules sitting in exactly those places where you would have those always pos edge constructs in Verilog, System Verilog. You have rules instead, and the thing about rules is they will have, like I said, there's global atomicity guarantee. Okay, so let me tell you a little bit about build flows. How do you compile and run BSV programs? So this picture shows you the kinds of different things you can do with it. So right at the top, first of all, your source code can be in BSV or in BH. foo.bsv, baz.bs. BS here does not stand for bullshit. It stands for Bluespec, unfortunately. And those two, you can take individual packages and run it through the BSC compiler, which is just a standard like CC or any of your favorite compilers. It's just a command line call to call BSC with the names of files you want to compile and flags and things like that. And there are two ways you can go with that compile. one way is shown on the far left here, and let me first talk you through that, which is that it produces some intermediate files. We call them .bo and .ba files. It's just some intermediate form. And then we can take it through a second pass of BSC, which is a link pass, which will take that and then produce. It actually goes via C and C++ into native machine code, so that produces for you a simulation executable. Now, one of the things you can do in both the BSC and BH is you can import C or C++ files. So you can provide your other C, C++ files along with the BSC link, and it will compile them all together into the executable. So that's one part, which is basically simulation through our own compiler and linker. I shouldn't say our own linker. We compile into C, C++, and then use the standard GCC-like linkers for producing the final executable. So this is just standard C++. You can import very easily with a one-liner. You can import a C function into BSV as a C function. And so we often use that either for test benches. The C code can do whatever it likes and produce stimulus test outputs, etc. Or we might do it even for design elements before we have refined them. In other words, we've decided the interface of the thing. We haven't yet filled in the BSV for its internals, but for the moment, we'll just import a C function to do whatever function it needs to do. So that's on the left. On the right here, we produce Verilog, and this is very vanilla, not even system Verilog. It's just vanilla Verilog that's produced out here, which is within the synthesizable subset of Verilog. And that Verilog, you can either take it to simulation or FPGA or ASIC. If you're going into simulation, once again, you can bring it in with other C++ files and other Verilog files that were existing IP or your handwritten Verilog files. And if you're going in for synthesis, etc., then you take your Verilog and the other Verilog files. Now, the thing I should say is that the BSC compile step at the top has already taken into account everything to do with scheduling constraints, etc., and made all the decisions about what is going to happen simultaneously within a clock. So that scheduling has all been done at this level. So by the time you get down here, there's none of that changes. So whether you run in so-called BlueSim simulation or Verilog simulation, or in actual hardware, you should get exactly the same cycle accurate behavior. There's no variation in that. Okay, so what are the main tasks that the BSC compiler actually does? So again, part of it should not be surprising for people who know Chisel. The microarchitectural state remains as in the source, right? In other words, which registers you have, what FIFOs, what register files, what SRAMs, etc., is whatever you said was in the source. There's no unpredictability out there. Plus local optimization. If BSC finds that you never write into a register, it might, and you just initialize it, it might convert that into a constant. Or if you never read from a register, it might just take it away, etc., etc. So, but there's a small local things. Computational computation that you had in your source, A plus B, or, left shift this by so much, etc. Those remain exactly the same all the way through. Once again, we might do some local optimizations, common sub-expression elimination, those kinds of things. And the most serious thing it does is the conversion of rules into Verilog RTL. And this is, if you think of a single rule, it's very straightforward, right? Which is, if you think of an always block, and then think of an if then else, where if has the rule condition in it, and the body of the if has the actions being performed by things. So in that sense, it's very straightforward. The big issue comes when you have multiple rules, and those rules are sharing state, and you have to preserve atomicity. So this is where most of the work of the compiler is in generating code, which is maximizing the concurrency of rules while preserving atomicity. In other words, it must look at all these rules. It must look at all the different state elements and what are the scheduling constraints, etc., and insert arbitration logic to make sure that we don't have either nonsensical logic like double writes into a register in the same clock, or unwanted logic because of the basic rule scheduling conditions. So this is logic that if you did not have atomicity, and you were writing directly in RTL, or I think presumably Chisel as well, is something you have to think about. If there are two guys who are both trying to enqueue into the FIFO, who wins on that? You have to think about that, and you have to express that somehow in the logic directly in the source itself. So this is the kind of logic that is produced by the compiler. It's all combination logic only. There's no new state added in this, and it does a lot of work in trying to optimize that logic. In particular, it uses an SMT solver internally to look at these Boolean conditions to be able to recognize, for example, that these two Boolean conditions, for example, are never true together, or they're always true together, or properties like that, which when you know that information, you can produce better and less expensive arbitration logic than if you didn't know those things. So that's basically the work of the BSC compiler, and the quality of the code is, and any such claim always is heard with and must be taken with a pinch of salt, comparable to hand-coded RTL. And what do I mean by that? You can get an intuitive sense of what I mean by that, because unlike HLS, for example, where initially you have no idea what RTL you're going to get out of the compilation process, here, most of it is not a surprise, right? The microarchitecture in terms of what are the state elements is not a surprise. The basic combinational logic that you express in the source, that's not a surprise. The arbitration logic is the only thing that's being added by the compiler, and that is logic that you would have written by hand anyway. And the only question is whether you would have written better that arbitration logic would have been better had it been handwritten versus what the BSC is providing. But that should give you a flavor of why, generally speaking, we're not concerned about the quality vis-a-vis writing the same thing by hand. Okay, so that's basically the end of my presentation per se. I want to conclude by saying there's a lot of topics that we don't have time to go into today. We barely scratched the surface. We've talked about some of the things on the left in a little bit of detail, and there are other things that I haven't mentioned here in any level of detail, like exactly how does this numeric types and bit width checking works. We've talked about rules and guarded atomic actions and the object-oriented interfaces. There is a sub-language within BSV called statement FSM, which allows you to express structured processes. So for example, if you're writing a test bench, the stimulus might be a loop that says, do this, do this, do this, then read this and check that, right? So you can think of that like almost like a sequential piece of code that just has to wait for the appropriate results to be available, etc. So that's what I'm calling a structured process. It might be a linear piece of code. It might do conditional branching. It may have while loops. It may have fork join parallelism in it. Those things, ultimately, everything can be expressed using rules. But when you have a structured process like that, you can automate some of the bookkeeping you have to do in terms of the state that sequences those rules and have that automatically generated for you. We import CRTL, interface with CRTL. There's an extensive set of libraries that are available, which are highly parameterized for reusability. We produce, as I mentioned, cycle accurate code, even in Bluesim. Even in Bluesim, you can generate VCDs from Verilog. Of course, you can generate VCDs. There's a $display statement. So for those of you who prefer debugging using printfs, you can do that in BSV. Now, also everything I've shown you is synthesizable. In other words, there's no concept of a synthesizable subset in BSV, modulo certain things. Of course, things like $display and all, which are not synthesizable in Verilog either, are not synthesizable into real hardware. But you don't have to restrict this set of the language you use when you're using BSV, which is something you have to be very careful of. Typically in HLS, certain stylized things are allowed in your C and C++ code, but not arbitrary stuff. I say readable RTL in quotes. We've done a lot of engineering work to do this, but it's partly true. In other words, the modules and module hierarchies are exactly what you would expect in the RTL from the source BSV. The interfaces look exactly like what you expect from the source BSV. The state element, the submodule instantiation, exactly what you'd expect from the source. The only part which can get a little inscrutable is the place where the compiler has put in this arbitration logic to manage atomicity of rules. That admittedly is not that readable. The other interesting tool that was produced actually at University of Cambridge is this tool called Bluespec. For those of you who know Haskell and know about quick check and the general field of property-based testing, the exact analogous tool can be written and has been written in Bluespec itself by people in Cambridge. And the nice thing about this Bluespec is that it's also synthesizable. So it actually can be run on an FPGA along with the design that you're testing. And it has all the usual features that you see in quick check, which is random generation of stimulus, sort of breadth first generation of that. And when it finds, and then it testing a property on each run, when it finds a counter example on a property, it does shrinking. So you can then start shrinking the stimulus so that it tries to produce a minimal stimulus that exhibits the same failure, etc. So all of this is what we think contributes to what we think of as agile hardware design, which I believe is the title of your course in BSV, which is that you can mix and match modules, you can refine modules. If you're into formal methods, you can go towards formal methods for rules and guarded atomic actions. You can do fast refactoring because of the expressive part of the language and because of rule atomicity. You can do safe refactoring, again, because of strong static type checks, atomicity, clock domains, and so on. So we're not intimidated by taking a large piece of code and refactoring it quite heavily. I shudder to do this in a language like Python because I never remember my constraints, and I find the bugs when I try running it. But in a strongly typed language and with a language with atomicity, you can be quite daring in the changes that you're willing to undertake. So repeating what I said earlier, these are the key points. And there's a slide here which has all the various links to compilers, online discussion topics. I have a textbook that I've written on BSV and designing a simple pipeline RISC-V CPU called Fife. You can find that on this website. There's lots of IP available, all free and open source on the web. Bunch of RISC-V CPUs. Cambridge University took we took MIT's RISC-V 000, which is a superscale order design, made some fairly small changes in it, which we call tuba, with a 000 in the tuba. And Cambridge took that, and they have added their Cherry security capabilities in that, and they're pretty active in the field of doing Cherry research on that. Cherry is now being standardized by RISC-V International as part of the RISC-V standard itself. You'll also find various kinds of IPs as shown out here. Okay, that's the end of my talk. I was noting with amusement that I use Beamer to make my slides, no pun intended. And I'll stop there, leaving these things. I think these slides will be available for you, so you can get the links later on and try them on. And I'll stop there.
Great, thank you. Let's thank the speaker. Open up for more questions. Yes, we have one.
So I'm curious, I think you mentioned that there is a SMT solver used for generating the arbitration logic. Is that consistent from compilation run to compilation run? Like, is that normally deterministic, or is there some degree of non-determinism that comes up with using the SMT solver to generate the arbitration logic?
I'm not sure I fully heard the question. You're asking about whether the SMT solver itself introduces some non-determinism, or?
Yep.
Yeah.
Where does non-determinism come from?
We're using the SMT solver basically to compare rule conditions. So when we have a different set of rules, a certain level of filtering happens in the sense that's, because of general natural locality of designs, rules, only small sets of rules typically interfere with each other, even though they may be across different modules, etc. And then when we have that set of modules, we look at the Boolean conditions that represent the conditions of those rules and getting additional information about those Boolean conditions, such as something is always true, something is always false. These two conditions are never simultaneously true. They can sometimes be simultaneously true. They can, things like that. Those are the questions we ask the SMT solver to do. And we take whatever its result is and we use that for improving the arbitration code that we produce. We have, I think that the SMT solver itself is parameterizable. I think Yikes is one of them, and Z, whatever from Microsoft, that's another one of them. You can plug in different SMT solvers into the compiler.
Great. One other question I had is, so if you're worried about frequency for your design, hopefully you have some help from CAD tools with things like register retiming. From the point of view of Bluespec, how can you assist with that process, or how do you go about frequency?
So I think at the top level, it's manual, just like it might be in, say, System Verilog, in the sense that if I'm designing a CPU pipeline, etc., how do I know it's going to meet all its measures? How do I know it's going to meet its area budget? How do I know it's going to meet its timing budget, etc.? And you don't, right? So area, you can it's not that different from Verilog or System Verilog in the sense that you're specifying the state, so you have some sense of that. But timing is something you don't. So so that's unfortunately a long and somewhat painful feedback loop, which is you build your design, you run it through your synthesis tool, and you get your timing report. And the first level of unfortunateness is that the timing report will be on the Verilog, not on your BSV source code. So, but we've done a pretty good job of not doing unnecessary name mangling, etc. So it's usually fairly clear from the timing report where that critical path problem is in your BSV source code. So when you know what the issue is from that level of analysis, then you have to refactor. And we don't have any automatic tools at the moment for that. In principle, it's the nice thing about the whole rule mechanism is it's possible, but we haven't had the resources or the time to be able to produce such a tool like that. But we're not doing automatic retiming or refactoring or anything. It's a manual process of saying, okay, this stage has too much work in it. I have to split it into 2 stages, for example. And that's a manual process right now. The only thing that the language helps you there is that because of the types and the atomicity, etc., that refactoring is often, it's done manually, but it's not difficult to get it done correctly.
Great. That sounds good. Well, thank you. I think we're about out of time here, so we're going to close it down. Thanks again. Stop the recording.